June 8th, 1783. Before sunrise, the highlands of Iceland were exactly what they had been for generations: cold, remote, quiet. Then the ground began to move. It did not explode like a mountain. It tore. A crack opened across roughly 27 kilometers, about 17 miles, of wilderness, splitting the earth in a line of fire that seemed to have no end. For the people living nearby, this was only the beginning. During the first 12 days, lava poured from the fissure at a rate equivalent to roughly 2 Olympic swimming pools of molten rock every second. The eruption would continue for 8 months. It would release around 122 million tons of sulfur dioxide into the atmosphere, roughly 80 times more than Mount St. Helens released. And the lava was not the worst part. The lava could be seen, the gas could not. Within weeks, a strange sulfurous fog spread across Europe, reaching from Britain to France, Germany, and beyond. People breathed it without knowing what it was. In Britain alone, an estimated 23,000 people died from the polluted air. And thousands of kilometers away, in Paris, Benjamin Franklin, the then American ambassador to France, looked at the strange haze hanging over Europe and reached a conclusion that was decades ahead of its time. A volcano could change the climate far beyond the place where it erupted. In Iceland, a Lutheran priest named Jon Steingrimsson recorded the eruption in extraordinary detail while lava advanced toward his church. His account is still studied by volcanologists more than 2 centuries later. Today, we're returning to the eruption of 1783 to uncover what actually came out of that enormous fissure, how its invisible gases transformed the atmosphere across Europe, and why an eruption that began in one of Earth's most isolated landscapes may have helped reshape the history of an entire continent. Iceland begins with a line drawn through the middle of the Atlantic, where two immense pieces of Earth's crust are moving apart. The mid-Atlantic ridge reaches the surface here, marking the boundary between the North American plate and the Eurasian plate. Each year, the plates separate by roughly 2 centimeters, which is about 3/4 of an inch. The movement is almost imperceptible from the ground, yet it continually creates space for molten rock to rise. Another source of heat lies beneath the island. A mantle plume, meaning a rising column of unusually hot rock from deep within Earth, feeds the region with additional magma. This combination of spreading crust and deep heat has made Iceland one of the most productive volcanic regions on the planet. Although the island occupies only a small fraction of Earth's surface, it produces roughly a third of the lava that reaches the surface each year. The landscape created by this process can make the distinction between mountain and volcano seem less important, because the island's volcanic architecture extends far beyond the cones visible from the surface. Some eruptions gather around a single opening and build a cone layer by layer. Others follow weaknesses that stretch through the crust. These are fissure systems, networks of fractures and underground pathways that can open at many points along the same zone, allowing magma to reach the surface across a broad stretch of land. Laki belongs to one of these larger volcanic networks. The fissures are connected to the Grímsvötn volcanic system, whose magma storage and pathways extend beneath Vatnajökull, Iceland's enormous ice cap. The ice above this system adds another dimension to the landscape. Heat from below can interact with enormous quantities of frozen water, while pressure within the crust continues to shift as magma moves through fractures. For centuries, people living around Iceland learned to farm within this restless geography. By 1783, roughly 50,000 people lived on the island. Most depended on sheep, cattle, horses, fishing, and small-scale agriculture. Food production was local, seasonal, and closely tied to the condition of pasture and weather. A failed season could reach directly into a household's stores, leaving little distance between hardship and hunger. Iceland was also governed under Danish rule, and trade was tightly controlled through a Danish monopoly. Most commerce passed through designated coastal trading posts, limiting the ability of Icelandic communities to respond quickly when local supplies failed. There were no modern food reserves waiting in warehouses, no rapid transport network, and no global market capable of shifting grain across oceans within days. That made the island's geology part of everyday survival. The same forces that continually built new land also shaped the limits of what people could grow, store, and preserve. A volcanic system could remain dormant for generations, while its underlying pathways continued developing, gathering pressure and magma in places no farmer could see. By the summer of 1783, Iceland therefore held an unusual combination of conditions. A spreading plate boundary provided fractures, a deep mantle plume supplied heat, a connected volcanic system gave magma multiple routes upward. Human communities, meanwhile, depended on a narrow biological margin for food. The landscape could absorb ordinary disturbances. A prolonged eruption across many openings would test every part of that margin at once. For several days, the highlands carried a warning that could be felt before its meaning was understood. Small earthquakes passed through the ground in clusters, each one marking movement below the surface. They were the kind of disturbances that accompany magma forcing its way into fractures, gradually changing the pressure within the crust. To people living nearby, they belonged to a landscape already shaped by earthquakes and volcanic activity, and their significance could only become clear afterward. On June 8th, 1783, shortly after sunrise, the pattern changed. The crust began to split along a line that would stretch far beyond the scale of an ordinary volcanic vent. Cracks opened in succession, allowing fire to appear through openings scattered across the highlands. Onstein Gremson, watching from the region, described the earth swelling with tremendous howling before the surface shattered. Flames rose from small openings, while blocks of rock were thrown upward to heights he could scarcely describe. Within hours, the active fracture had extended for roughly 27 kilometers, which is about 17 miles. More than a dozen openings were producing fountains of molten rock along the developing fissure. Each vent added another source of heat and light, while the ground between them continued to fracture and shift. From a distance, the eruption could have seemed like a single event stretched across the landscape. In reality, it was a chain of connected openings, each drawing from the same rising supply of magma. The lava itself had a particular character. Basaltic lava contains relatively little silica, which keeps its molten structure fluid enough to travel readily across sloping ground. Instead of piling into a steep cone around one opening, it can spread outward in broad streams, following valleys and low places. At Laki, these streams began moving downslope through terrain used for grazing and farming, carrying enormous amounts of heat into places where people depended on the land. The eruption also altered the water flowing through those valleys. Heat from the molten rock melted nearby ice and snow, adding sudden volumes of water to rivers and channels. Lava advanced through the landscape, while cold floodwater moved alongside it, sometimes carrying loose sediment and debris downstream. The two processes belonged to the same eruption, yet they affected the land in very different ways, one covering it with rock and the other reshaping channels beneath the surrounding slopes. During its first 12 days, the eruption reached an extraordinary rate of output. The amount of molten basalt emerging each second was comparable to roughly 2 Olympic swimming pools. Over those early days, the landscape received such a continuous supply of lava that individual flows merged into larger fields, spreading across the countryside and preserving the shape of channels, ridges, and valleys beneath layers of new basalt. Sound filled the region as well. Witnesses described a persistent roaring that could be felt through the ground as much as heard through the air. It came from many sources at once, from fountains, collapsing rock, flowing lava, and the pressure of gases escaping through the fractures. The eruption had transformed the highlands into a place where movement was everywhere, beneath the feet, across the surface, and through the air. The familiar boundaries of the countryside were becoming difficult to recognize, as each new opening altered the ground and redirected the paths of water. Some eruptions announce themselves in a single violent interval, then leave a landscape that can begin settling almost as soon as the ash has fallen. Laki followed a different rhythm. Its activity unfolded in episodes, with periods of explosive fire followed by long outpourings of lava. The eruption behaved less like one event than a sequence of connected openings, drawing from a continuing supply below the ground. During the first 5 months, scientists have identified at least 10 major explosive phases. Each phase began with ash and volcanic gases rising above the vents, followed by sustained fountains of molten basalt. As the fountains continued, lava spread outward in broad streams. Some episodes lasted for days, while others continued for weeks, allowing enormous quantities of rock to accumulate across the highlands. The pauses between episodes were part of the eruption's structure. A reduction in activity at one location did not mean the underground supply had disappeared. Pressure and magma movement continued through the connected system, allowing the next opening to develop farther along the fracture. The pattern of activity also shifted along the fissure. When one portion became less active, another part of the fracture could open farther along the system. Magma, therefore, reached the surface through changing groups of vents instead of remaining concentrated around one opening. The landscape became a moving arrangement of separate eruption sites, connected underground while behaving differently at the surface. By February 7th, 1784, the eruption had continued for 8 months and one day. The fissure zone had reached roughly 27 kilometers, which is about 17 miles, and activity had occurred through approximately 135 vents spread along that distance. Each opening added its own fountain, flow, and deposit, while neighboring lava streams sometimes merged as they traveled across the terrain. Seen from above, the arrangement would resemble a long chain of volcanic mouths scattered across the land. Some produced active fountains, while others fed streams, moving away from the fracture. Lava from different directions could meet in broad sheets, filling hollows and crossing older flows. The scale becomes easier to grasp through the final volume. Laki produced about 61 cubic kilometers of basaltic lava, that is nearly 15 cubic miles, covering roughly 1,450 square kilometers, which is about 560 square miles. The explosive phases also sent columns of ash and volcanic gases far above the immediate eruption zone. At their highest, these columns reached roughly 14 to 21 kilometers, which is about 9 to 13 miles. At those elevations, material could enter the upper atmosphere and encounter powerful currents capable of carrying particles far from Iceland. The eruption, therefore, had a vertical structure as well as a horizontal one, spreading through the crust, across the surface, and upward into the atmosphere. Its intensity can also be described through the Volcano Explosivity Index, a scale used to compare the magnitude of explosive eruptions. Laki reached level 6 on that scale, placing it in the same broad category as the eruption that formed the Crater Lake caldera. The distinction lies in how that energy was delivered. Laki distributed its activity across 8 months, allowing lava, ash, and volcanic gases to accumulate through repeated episodes. The eruption became a prolonged geological process, with one opening after another participating in the same enormous release. The most consequential material rising from Laki could not be seen from the ground. While rivers of basalt spread across Iceland, the eruption was also feeding enormous quantities of volcanic gases into the atmosphere, where their effects could travel far beyond the reach of the lava. Among those gases was sulfur dioxide, a reactive compound released when sulfur-bearing material from the magma entered the air. Laki produced an estimated 122 million tons of sulfur dioxide during the eruption. For comparison, the 1980 eruption of Mount St. Helens released about 1 million tons. Laki therefore sent roughly 80 times as much sulfur dioxide into the atmosphere, despite the very different ways the two eruptions unfolded. Sulfur dioxide itself was only the beginning of the atmospheric transformation. High above the ground, it encountered oxygen and water vapor and underwent chemical reactions that converted much of it into sulfuric acid. The acid formed extremely small particles and droplets, together known as sulfate aerosols. Their size allowed them to remain suspended in the atmosphere for long periods, giving the material time to spread across enormous distances. Laki was also releasing other gases with more immediate consequences near the ground. Around 15 million tons of hydrogen fluoride entered the atmosphere, along with roughly 7 million tons of hydrogen chloride. Hydrogen fluoride was especially important for Iceland's pastures because it could settle onto vegetation and become concentrated in grazing animals. Hydrogen chloride contributed to the acidity of moisture and precipitation, adding another source of chemical stress to soil, fresh water, and plants. The sulfur compounds followed a different path. As the eruption columns rose, some of the material reached the upper troposphere and lower stratosphere, where atmospheric circulation could carry it away from Iceland. Instead of remaining concentrated around the fissure, the aerosol became part of a moving layer of particles suspended high above the surface. Scientists estimate that the eruption ultimately produced around 200 million tons of sulfuric acid aerosol. That number represents an immense quantity of material distributed through the atmosphere rather than sitting in one place. Individual particles were microscopic, yet together they altered the way sunlight traveled through the air. Incoming sunlight could be scattered by the aerosol before reaching the ground, changing the amount of solar energy available at the surface. The altitude of the material also mattered. Air movements high above the weather systems near the surface could carry the aerosol across the Northern Hemisphere. The particles did not need to remain directly above Iceland to continue affecting the atmosphere. Their distribution widened as winds transported them into regions where people had no connection to the eruption and no reason to associate the altered sky with a volcanic fissure thousands of miles away. The particles could remain aloft long after the original gas had left Iceland for months. Above Iceland, during the summer of 1783, the atmosphere was therefore becoming chemically different from the air that had surrounded the island before the eruption. Sulfur dioxide was being transformed into suspended sulfuric acid particles, while other volcanic gases added further chemical stress to the environment. The eruption had begun at the surface, yet part of its most consequential output was now traveling through the sky, carried far beyond the boundaries of the lava field. Pastures became the first places where the chemistry of the eruption could be felt. Hydrogen fluoride, released with the volcanic gases, settled onto vegetation and soil across Iceland. Once deposited on grass, the fluorine could enter the bodies of grazing animals. The danger traveled through an ordinary act of survival. Feeding, a field that had sustained generations, could become hazardous without changing its color, texture, or familiar appearance. Fluorosis, meaning poisoning caused by excessive fluoride exposure, develops through damage to teeth and bones. In animals exposed to heavy contamination, the first signs could appear around the mouth, with teeth becoming weakened and eventually loosening. Continued exposure affected the skeleton, joints, and internal organs. The progression was gradual enough that a herd could continue grazing while its condition deteriorated. Sheep were especially vulnerable because they relied so heavily on pasture. Cattle and horses were exposed through the same landscape, each animal taking in contaminated vegetation day after day. There was little opportunity to separate the animals from the source. The grass still looked like grass, and hunger continued to drive livestock toward it. Accounts from the period describe changes that were difficult to mistake once they became advanced. Animals developed swollen joints and weakened bones. Their teeth deteriorated, making eating increasingly difficult. Some developed severe swelling around the head and jaw. Hair and manes could loosen, while damage to the skin and internal organs accompanied prolonged poisoning. The physical decline unfolded over weeks, turning familiar farm animals into visible records of a chemical process no one could yet explain. The tragedy deepened through repetition. An animal weakened by fluorine still needed food, so it returned to the same pasture. Each mouthful added another small dose. Each day extended the exposure. Farmers could watch a healthy herd become thin and unsteady, then lose the ability to feed itself properly. Moving animals to safer ground could help in some places, yet the contamination covered enough pasture that escape was difficult. There were few unaffected grazing areas, large enough to support entire herds, especially as the eruption continued to add new contamination. By the end of the crisis, approximately 79% of Iceland's sheep had died. Horses suffered a mortality rate of about 76%, while cattle losses reached roughly 50%. These figures represented more than the disappearance of individual animals. Sheep supplied meat, milk, wool, and breeding stock. Horses provided transportation and labor. Cattle contributed food and dairy products. The loss of so many animals removed several parts of the rural economy at once. Water systems were affected as well. Acidic conditions developed in some rivers and ponds, harming fish and reducing another source of food. Communities that depended on fishing therefore faced pressure from the same eruption through a different pathway. The landscape was becoming difficult to use, even where the surface appeared familiar. The food crisis that emerged in Iceland was therefore rooted in ecological damage. Pasture remained visible, yet much of it had become dangerous. Rivers still flowed, yet some could no longer support the fish that communities depended upon. Livestock remained in fields, yet many were carrying a poison that was gradually weakening their bodies. The disaster worked through the ordinary connections between soil, grass, animals, water, and people, removing one link after another until the island's food system had lost much of its foundation. The name given to the catastrophe was Mathu Harðindin, the famine of the mist. It described a season when hunger became woven into the landscape itself. The fields still existed. Fishing waters still bordered the settlements, and people still tended whatever animals remained. Yet, the foundations of ordinary life had been stripped away, leaving families to search for food within an economy that had almost no reserve. In 1783, Iceland was governed as a Danish dependency, and trade operated through a strict monopoly. Licensed Danish merchants controlled commerce at designated coastal posts, limiting the ability of Icelanders to obtain provisions from elsewhere. In a crisis that demanded rapid movement of food, this system offered few routes for relief. Ships could carry supplies, yet arranging those shipments required decisions and administration across a considerable distance. Weather, sailing schedules, and the difficulties of reaching scattered settlements could turn a shipment into a delay of weeks. For families already measuring food by handfuls and portions, those weeks carried their own weight. The timing made the shortage harder to endure. Much of the population depended on sheep, cattle, horses, and fish, so the loss of livestock removed meat, milk, wool, transport, and breeding stock at the same time. Fishing could still provide nourishment in some districts, but contaminated waters and disrupted conditions reduced what communities could draw from nearby rivers and ponds. Food, therefore, became a matter of stretching whatever remained from one day into the next. Old stores became precious, and every usable source of nourishment acquired greater importance. What had once been an ordinary meal could become the difference between maintaining strength and entering another day weakened. Hunger also changed the way disease moved through communities. People who had spent months breathing volcanic haze and living with reduced food supplies entered winter with diminished strength. Malnutrition weakens the body's defenses, making infections more difficult to withstand. As winter settled over Iceland, contagious illnesses added another burden to households already struggling to maintain enough nourishment for children, parents, and older relatives. The death toll reached roughly 9,000 to 10,000 people, close to one-fifth of Iceland's population. Each loss represented a household, a farm, or a small community becoming less able to care for those who remained. The population decline was so severe that recovery took decades. Births could replace some losses, but rebuilding a society also required animals, working horses, productive farms, and enough food to support another generation. The scale of the crisis reached the highest levels of Danish administration. Officials seriously considered whether Iceland's remaining population should be evacuated to mainland Denmark. Such a proposal reveals how thoroughly the eruption had altered the island's prospects. Moving an entire population across the sea would have been an enormous undertaking, yet the fact that it entered formal discussion shows how close the authorities believed Iceland had come to becoming unviable. The proposal was rejected, and the people remained. Survival came through scattered farms, fishing, whatever livestock escaped the worst contamination, community cooperation, and limited assistance from Denmark. 4 out of every 5 Icelanders lived through the famine, even though the society around them had been reduced to a fraction of its former security. The famine of the mist, therefore, became more than a record of mortality. It became a measure of how much human life could endure after the systems supporting it had been worn away. In the village of Kirkjubajarkloster, one man continued his ordinary responsibilities while the landscape around him changed. Jon Steingrimsson was a Lutheran priest whose parish stood along the path of the advancing eruption. His position placed him close to the physical destruction, yet his role gave him another task as well. He became an organizer, record keeper, and advocate for people whose usual sources of food and security were disappearing. Steingrimsson kept careful notes as events unfolded. He recorded when new fissures opened, how lava moved across the terrain, changes in the ash, the condition of animals, and the health of his congregation. Dates and sequences mattered to him. His writing carried religious meaning, but it also preserved observations with chronological detail and extraordinary careful attention. Each entry fixed a moment in time, allowing later readers to follow the eruption through the eyes of someone who had remained close to its changing course. That record became especially vivid on July 20th, 1783. About 6 weeks had passed since the eruption began, and a lava front had been advancing toward Kirkjubejarkloster. On that morning, the molten rock approached the settlement and reached the edge of the area around the church. Steingrimsson and his congregation gathered inside, while the advancing flow remained close outside. He began the service as the eruption continued around them. The congregation heard the movement of the earth, while he delivered what later became known as the fire sermon. His words were shaped by his faith and by the immediate circumstances surrounding his parishioners. The service gave the community a place to gather while the landscape outside was being altered by forces no person there could control. When the service ended, the congregation emerged to find that the lava had stopped. The flow had reached the church area and halted before passing through the settlement. For those who had been inside, the timing carried a powerful meaning. Many believed that Steingrimsson's prayers had protected them. The account became part of his identity, and later generations remembered him as the fire priest. Modern geology offers a physical explanation for the pause. Lava flows respond to the shape of the ground, and a stream can lose momentum when it reaches flatter terrain or when its supply decreases upstream. In this case, the advancing flow had reached the end of a natural topographic channel, while activity feeding it temporarily weakened. The geological process explains the movement of the lava, while the human meaning of the moment belongs to the people who witnessed it. Steingrimsson continued documenting the eruption because he understood that such an experience could disappear from memory. His fire treatise remained with his descendants for more than a century, passing through generations before it was finally published in 1913. By then, the world of the eruption had changed, yet the observations remained valuable. The manuscript preserved details that instruments of the 18th century could never have recorded, including the sequence and timing of volcanic activity and its effects on the surrounding community. His work survived because someone kept the pages. Long after the lava cooled, those pages allowed later generations to return to the eruption through a witness who had stood close to its path and written down what he saw. Across Europe, the summer light began to change in ways that were difficult to place. In late June of 1783, reports of an unusual haze appeared across France, Britain, Germany, and the Netherlands. The air seemed different from ordinary weather. Visibility was reduced, the sunlight looked altered, and a sulfurous smell lingered around towns and countryside. People had familiar words for fog and smoke, yet this haze behaved differently from either. It could persist through the day instead of dissolving with morning warmth. It could remain over a region without resembling smoke from a nearby fire. The strange appearance gave the atmosphere a quality that observers struggled to describe with the language available to them. Across widely separated places, people were recording similar changes without realizing they were witnessing the same event. The reports eventually formed a remarkable geographic pattern. Accounts of the haze appeared from Iceland across continental Europe and as far south and east as Syria. That reach was difficult to understand in an age when information traveled by ship, horse, and handwritten letter. A person observing the altered sky in one country could have no immediate knowledge that another observer, hundreds or thousands of miles away, was seeing something similar. European natural philosophers offered explanations that reflected the scientific ideas of their time. Some considered whether volcanic activity far out in the ocean might be responsible. Others wondered about unusual atmospheric disturbances, celestial influences, or changes in the substance then believed to fill space, known as the ether. These ideas were attempts to give a recognizable cause to an unfamiliar phenomenon. The connection between a volcanic eruption in Iceland and atmospheric conditions across Europe was still outside the accepted framework of natural science. The appearance of the sun became one of the most distinctive features. Observers in Britain, France, and Germany described the solar disk taking on deep red and copper tones even around midday. Sunlight passing through the suspended particles was scattered and filtered, changing the balance of colors that reached the ground. Fields, buildings, and roads could take on an unusual reddish or coppery illumination, giving familiar landscapes a different appearance. The same particles that altered the sunlight were part of the sulfuric acid aerosol produced by the eruption. Enormous quantities had entered the atmosphere above Iceland, and atmospheric circulation carried the material across the Northern Hemisphere. The particles were small enough to remain suspended for extended periods, allowing their influence to continue while the source of the eruption remained far away. For people living through that summer, the haze became part of ordinary life. Diaries and observations recorded its persistence, its smell, the altered appearance of the sun, and the strange color of the daylight. Artists noticed the unusual skies as well, preserving impressions of a world illuminated through a changed atmosphere. No single European explanation could yet connect all these observations into one coherent event. The same volcanic material was appearing in different records under different descriptions, separated by language, distance, and uncertainty. Above the fields and towns, the atmosphere carried evidence of an eruption whose source many observers had never seen, while the altered light reached places that had no idea how far away its origin lay. Each day brought the same unfamiliar light, allowing the atmosphere itself to become a record of distant volcanic activity written across the sky. The summer of 1783 carried a strange burden through the streets and villages of Europe. People woke beneath altered skies, breathed unfamiliar air, and found their bodies responding before anyone understood the cause. Physicians in Britain and France recorded recurring complaints of headaches, burning sensations in the chest, difficulty breathing, and eyes that watered and stung. The symptoms appeared across communities separated by great distances, following the same atmospheric disturbance. Doctors could treat individual complaints, yet the shared cause remained beyond their reach for the entire season. The haze contained sulfuric acid aerosol, formed when sulfur dioxide from the eruption reacted with moisture in the atmosphere. These particles were small enough to remain suspended while people breathed the surrounding air. At sufficient concentrations, sulfuric acid aerosol can inflame the respiratory system, irritate the eyes, and place additional strain on people whose lungs were already vulnerable to illness. In 1783, there was no modern system for measuring particulate pollution, no air quality network, and no understanding of the distant volcanic source. Britain recorded an especially striking increase in deaths during the summer. Historical research has estimated that around 23,000 additional deaths may have been associated with the polluted air, particularly among vulnerable people and during periods when the haze was strongest. Contemporary observers had no volcanic explanation to connect these deaths with Iceland. They spoke instead of a pestilential fog, giving a name to the condition without knowing what had created it. French records preserve another way of tracing the disturbance. Parish registers recorded births, deaths, and other events in local communities, creating a scattered record that could later be compared across seasons. Historians and scientists studying these records found evidence of excess mortality during the summer and autumn of 1783. The pattern did not appear as one single catastrophe in every village. It emerged through many small increases, repeated across different communities, revealing how a distant atmospheric event could leave a human signature in ordinary records. The same air carried consequences into the fields. Acidic moisture reached the ground as rain and deposited material onto vegetation and soil. Crops could be damaged without being destroyed in one dramatic moment. Leaves were injured, growing conditions became less favorable, and harvests could fall when households had little room for shortage. Across northern Europe, food production was already tied closely to seasonal weather, so even modest reductions could become important when combined with illness, weakened livestock, and disrupted rural work. For many who survived the polluted air, the experience may have felt less like one overwhelming event than a season of persistent physical strain. Breathing could become harder, eyes could burn. Work in fields and workshops demanded effort from bodies already coping with poor air and reduced food supplies. The summer seemed to carry an unusual heaviness, while the connection between sky and sickness remained unknown. Above those fields, another process was already underway. Sulfuric acid aerosol scattered and reflected part of the incoming sunlight, reducing the solar energy that reached Earth's surface. The change was gradual, spread across enormous regions, and difficult for anyone living through the summer to recognize as a single physical process. Yet the atmosphere had begun altering the balance between sunlight and the ground, turning a distant eruption into a planetary disturbance felt through breath, harvests, illness, and the changing quality of daylight. Benjamin Franklin was 77 years old in 1783, living in Paris as the American ambassador to France when the strange haze entered his observations. He had spent much of his life studying natural forces, from electricity and lightning to the movement of air and heat. His habit was to watch patiently, compare one observation with another, and search for relationships that might otherwise remain scattered across separate events. Paris gave him a distant window onto the disturbance. The haze lingered through the summer, changing the character of daylight and making the sun appear weakened. Franklin also noticed an unusual chill developing as the season progressed. The atmosphere seemed to stand between the sun and the ground, allowing light through while reducing some of its warmth. For a man accustomed to thinking about circulation and energy in nature, the coincidence between the altered sky and changing temperatures offered a clue worth preserving. During the spring of 1784, Franklin presented an account proposing that the severe winter of 1783 to 84 across Europe and North America had been influenced by a veil of vapor produced by volcanic activity in Iceland. His explanation was built from observations available to him. He could not describe the chemistry of sulfur dioxide becoming sulfuric acid aerosol. The word aerosol itself had no place in his vocabulary. There were no satellites watching the atmosphere, no global network of instruments, and no computer models capable of tracing particles across an ocean. Even so, the central idea reached remarkably far. Material released by a distant eruption could alter the amount of sunlight reaching the surface, which could then affect temperatures across an enormous region. Franklin was connecting events separated by thousands of miles through the behavior of the atmosphere. His reasoning belonged to an older tradition of careful natural observation, yet it pointed toward a distinctly modern understanding of Earth as one connected physical system. Franklin was not the only observer moving in this direction. A French naturalist, Morgue de Montredon, had reached a similar interpretation slightly earlier from his own observations. Their independent conclusions mattered because they emerged from different places and different lines of attention. The haze was no longer merely an unusual feature of the summer sky. It could be treated as evidence of a physical process extending far beyond the eruption itself. The significance of Franklin's proposal rests partly in its measurable scale. In 1784, the possibility that one volcanic eruption could influence climate across an entire hemisphere was a striking extension of ordinary weather observation. Today, volcanic climatology studies how particles and gases released during eruptions interact with sunlight and the atmosphere. Climate science examines the same interconnected system on broader timescales, while geoengineering research considers whether deliberate changes to atmospheric processes might alter climate. Franklin's paper did not immediately transform scientific understanding. The mechanism remained incomplete, and many details would require observations and instruments that did not yet exist. Those missing pieces would later reveal how strongly the upper atmosphere could reshape conditions at the surface. Still, his record preserved a crucial insight. The sky above one island could become part of the climate story of distant continents, linking volcanic fire, atmospheric chemistry, sunlight, and winter through a single chain of physical processes. The atmosphere became the road by which Laki traveled beyond Iceland. A jet stream is a band of fast moving air that circles the Northern Hemisphere high above the ground, carrying air masses from west to east. These currents can flow at speeds approaching 200 miles per hour, forming broad pathways through the upper atmosphere, often between 6 and 9 miles above the ground. For material released high enough above the surface, distance itself becomes less important than the movement of the air. During the strongest phases of the eruption, ash and volcanic gases rose into towering columns. Some reached heights of 9 to 13 miles, placing sulfur dioxide within the levels where powerful upper atmospheric winds could seize it. Once carried into those currents, the gas no longer belonged to Iceland alone. The atmosphere became a moving system, transporting volcanic material across seas and borders without roads, ships, or human assistance. The journey changed the sulfur as it went. Sulfur dioxide encountered water vapor and underwent chemical reactions that produced sulfuric acid aerosol, made of extremely small particles capable of remaining suspended for months. Their size allowed them to travel with the surrounding air rather than falling quickly toward the ground. Wind patterns then spread the material unevenly, gathering it in some regions and thinning it across others. The veil was constantly shifting, yet its influence reached across much of the Northern Hemisphere. Those particles affected the planet in two connected ways. They scattered and reflected incoming sunlight, reducing the solar energy that reached Earth's surface. They also provided surfaces around which atmospheric moisture could gather, contributing to acidic precipitation when those droplets eventually returned to the ground. The same volcanic material could therefore influence both the light above a field and the chemistry of the rain falling onto it. The temperature records of the following winter reveal how far the disturbance had traveled, even though nobody watching a frozen river could see the volcanic particles that had helped alter the air. In the eastern United States, observers recorded a winter that was nearly 5 degrees Fahrenheit colder than the long-term average. Across Europe, rivers froze in places where such conditions had become unfamiliar. The Thames in London formed ice, while the Seine in Paris also froze. These were local expressions of a disturbance whose source lay thousands of miles away. A change of about 1 degree Celsius, or about 2 degrees Fahrenheit, in the average temperature of the Northern Hemisphere may appear modest when reduced to a single number. Spread across an entire hemisphere, however, that shift represents an immense rearrangement of energy within the atmosphere, oceans, land, and ice. A small change in an average can touch countless local conditions at once, altering the length of growing seasons, the state of rivers, and the demands placed upon people and animals. The remarkable part of this atmospheric journey was its lack of a visible path. No line could be drawn across the sky from Iceland toward Europe, Asia, or North America. The sulfur traveled inside moving air, transformed along the way, and became part of weather that seemed local wherever it arrived. A volcanic eruption had entered the circulation of the planet itself, carried eastward through currents that had been moving above human lives for centuries. A field can tell a story long before anyone writes it down. In France, the harvest of 1783 arrived after a season in which sunlight had been reduced and acidic moisture had touched vegetation across northern Europe. Grain still stood in many places, yet yields were diminished. Acidic rain and reduced sunlight placed additional stress on leaves during a season when crops were already dependent on every available hour of growth. For farming communities living close to the margin, a smaller harvest meant fewer sacks carried into storage, higher prices at market, and less protection against the months ahead. The change was especially difficult for rural families whose daily food depended heavily on bread. In 18th century France, workers could spend a large share of their income on bread and flour, leaving little room when grain prices climbed. A modest shortage could therefore become a much larger hardship. The mathematics of hunger were painfully direct. When the price of a loaf rose, families could not reduce their need for food in the same proportion. The cold season added another burden. Winter wheat had already been planted across French farmland, intended to become part of the following year's food supply. Severe winter conditions damaged these young crops in many areas, leaving farmers with the memory of a poor harvest behind them and uncertainty in front of them. The agricultural system was being asked to recover while its reserves were already strained. A weak harvest could therefore echo through an entire winter. Years later, France encountered another sequence of weather extremes. In the spring and summer of 1788, severe drought affected large parts of the country, and grain production fell well below normal levels. Then, on July 13th, a powerful hailstorm crossed broad areas of France, damaging fields and vineyards. The storm was followed by a harsh winter beginning late that year, with prolonged freezing conditions extending into early 1789. These events were independent of Laki in their immediate causes, yet they struck a society that had already endured years of economic and agricultural pressure. By this point, grain prices had become deeply connected to the stability of everyday life. Bread riots began appearing in several regions during the food shortages of 1788, while rising prices placed greater pressure on laborers and poor households. Markets could absorb a small disruption when supplies were healthy. They became far less forgiving when harvests repeatedly arrived below expectation. The connection between Laki and the crisis of 1789 therefore needs care. The eruption did not create the French Revolution by itself, and historians do not treat it as a single cause. Its effects formed one thread within a larger fabric of debt, inequality, political conflict, poor harvests, and repeated weather disasters. The eruption weakened food security during a vulnerable period, while later drought, hail, and winter cold added new strain. By the spring of 1789, the memory of earlier shortages had become part of a much larger crisis. Farmers were watching the fields, merchants were watching prices, and families were watching the amount of bread their wages could buy. A volcanic disturbance that began in Iceland had become one element in a chain of environmental and economic pressures reaching into the heart of France. On the morning of July 14th, 1789, Paris was already carrying years of strain. Crowds moved through streets where the price of bread had become inseparable from the question of survival. When the Bastille was stormed, the people there were responding to immediate political and economic pressures, shaped by a much longer history of inequality, debt, taxation, and scarcity. The French Revolution had many causes, and the strongest historical explanations remain rooted in the structure of French society. The monarchy was deeply indebted. Taxes were unevenly distributed. Political representation was contested, and Enlightenment ideas had given educated Europeans new ways to speak about rights and government. None of these forces depended upon a volcano in Iceland. They had been developing for decades. Food, however, connected those larger tensions to ordinary life. Bread formed the foundation of the French diet, especially for workers and poorer families. When grain became expensive, wages could no longer stretch as far. Hunger transformed an abstract economic problem into something felt at every meal. The Estates General was summoned in a country already burdened by financial crisis and severe food shortages, and its meetings soon became the National Assembly. Laki belongs within this wider sequence as one contributing disturbance. Its eruption in 1783 disrupted growing conditions and weakened food security during a vulnerable period. The difficult winter that followed added pressure, while later weather extremes damaged harvests again. By 1788, France faced a disastrous agricultural season, and grain prices rose sharply. The food system had less resilience than it might have possessed under more favorable conditions. Climate historians and volcanologists have therefore examined Laki as a possible part of the chain connecting environmental disruption with political instability. The sequence can be traced through several stages, from volcanic aerosols and altered climate to damaged harvests, reduced reserves, rising grain prices, and increasing hardship. Each stage had other influences as well, and none operated alone. Political decisions, economic conditions, population growth, and social inequality shaped the outcome at every point. The distinction matters. Laki did not cause the French Revolution in any direct or singular sense. A volcanic eruption cannot explain the collapse of an old political order by itself. What it could do was narrow the margin within which a society could absorb another shock. When harvests failed again, when bread became harder to afford, and when trust in government was already fragile, that reduced margin became historically important. The people who gathered in Paris knew nothing of sulfur drifting from Iceland. The deputies who debated the future of France had no knowledge of atmospheric particles crossing Europe years earlier. The farmers struggling with poor harvests could not have traced their difficulties back to a fissure hundreds of miles away across the sea. Cause and consequence sometimes travel through systems too large for any individual to perceive. A change in the atmosphere can touch a field. A field can affect a market can strain a household, and thousands of strained households can alter the course of a nation. Laki was one thread in that immense fabric, almost invisible to the people living through it, yet woven into the conditions of a world approaching transformation. The connection is therefore indirect, cumulative, and difficult to see from the ground. Its importance lies in how environmental shocks can amplify pressures already present within human institutions. For most people in the 18th century, catastrophe had a shape. It arrived as a battlefield, a shipwreck, a fire, or a storm. Laki belonged to another category, one that was much harder to remember because its effects were scattered across seasons and societies. The eruption produced an extraordinary quantity of sulfuric aerosol, estimated at about 80 times the amount produced by Mount St. Helens in 1980. The material remained in the atmosphere for months, spreading pollution across the Northern Hemisphere. The comparison with Krakatoa is revealing. When Krakatoa erupted in 1883, enormous waves and hot volcanic flows killed tens of thousands of people in a concentrated disaster. News traveled rapidly by telegraph, and newspapers transformed the eruption into a global event almost immediately. Its violence had a recognizable center and a date that could be marked. Laki offered no such moment. Its damage accumulated through ordinary days. People breathed contaminated air, animals weakened in Iceland, harvests suffered, and winter brought additional strain. Families experienced hunger at their own tables without knowing that an eruption hundreds of miles away had altered the conditions around them. A death from respiratory illness could be recorded without any mention of volcanic gases. A failed field could look like bad weather. A costly loaf of bread could appear to be a local economic problem. That separation between cause and experience shaped the memory of the disaster. In Iceland, the communities best positioned to preserve a detailed account had themselves endured enormous losses. Jon Steingrimsson's account survived, yet his fire treatise remained unpublished for 132 years. The delay meant that one of the clearest records of the eruption did not enter wider scientific discussion until long after the people who witnessed it were gone. Across Europe, the haze became part of daily life without becoming a single, understandable story. Observers described strange sunlight, illness, damaged crops, and unusual weather, while explanations remained uncertain. The atmosphere itself carried the evidence, but the chemistry connecting one region to another was beyond the scientific tools of the time. People could describe what entered their lungs and settled over their fields without identifying its source. The French Revolution eventually became the defining historical story of the late 1780s. Political historians naturally focused on monarchy, taxation, debt, inequality, and the struggle over representation. Those forces were real and powerful. Environmental pressures became easier to overlook when they formed only one thread among many. Laki slipped further into the background as the revolution transformed the political map of Europe. There is a strange lesson in that fading memory. The disasters most often remembered are concentrated events with photographs, monuments, famous survivors, or a single terrible day. Slow disasters leave a different archive. Their victims disappear into parish records, harvest reports, medical notes, and household accounts. Their causes are separated from their consequences by distance and time. Laki was immense, yet it left no single image capable of carrying its story. Its influence moved through air, soil, animals, crops, markets, bodies, and weather. By the time many of its consequences had become visible, the eruption itself was already becoming history. The event faded from memory precisely because there was no moment when the world could point to it and say, "This is where the disaster happened." Long after the haze had faded from European skies, Laki began to acquire another kind of life, this time inside scientific thought. The eruption offered an enormous natural experiment, preserved across records from several countries, in which a disturbance at Earth's surface altered the atmosphere above it and changed conditions far beyond the volcano itself. That connection would become increasingly important as scientists learned to treat the atmosphere as part of a single physical system. Benjamin Franklin's observations formed an early thread in that history. His 1784 paper proposed that volcanic material from Iceland had reduced the sunlight, reaching the ground, and contributed to the severe winter that followed. Franklin lacked the language and instruments needed to describe sulfuric aerosol formation, yet his reasoning pointed toward what scientists now call volcanic climate forcing, the process by which volcanic particles in the atmosphere can alter the balance of incoming solar energy and influence temperature. The idea gained another opportunity for comparison after Mount Tambora erupted in 1815. The following year became known as the Year Without a Summer. Frost damaged crops in parts of North America, snow appeared during unusual times in Europe, and harvests suffered across several regions. Mary Shelley spent much of that strange season indoors near Lake Geneva, where the unsettled weather helped create the setting in which she began writing Frankenstein. The eruption gave scientists another large event against which earlier observations could be considered. Krakatoa in 1883 added another chapter. El Chichon in 1982 provided another. Mount Pinatubo in 1991 became especially valuable because modern instruments could observe the atmospheric response with a precision unavailable to earlier generations. Each eruption supplied another piece of evidence about how volcanic material rises, spreads, reflects sunlight, and influences climate. Laki, recorded with older and less complete observations, could then be placed within a much longer sequence. That historical sequence became useful for atmospheric modeling and for separating volcanic signals from the many other forces that shape weather and climate across time. Scientists could compare reconstructed sulfur emissions with observations of aerosol spread and temperature changes, testing whether computer simulations reproduced the broad behavior recorded in the past. Laki became particularly valuable because its effects were large enough to leave traces across many regions, while surviving records offered independent evidence from weather observations, harvest reports, and descriptions of the atmosphere. There is something fitting in that transformation. The eruption was difficult for people of the 18th century to interpret precisely because its most important effects were dispersed through the air. Centuries later, that same dispersal became part of its scientific value. A volcano had provided evidence that the atmosphere could carry the influence of an eruption across continents and alter the climate far from its source. Modern climate science now treats major eruptions as important tests of atmospheric behavior. Their particles provide measurable disturbances against which models can be compared, helping researchers examine circulation, radiation, chemistry, and temperature response. Laki therefore occupies an unusual place in the history of discovery. Its original witnesses saw fragments of a strange summer. Later scientists assembled those fragments into a physical story. The eruption that once seemed to vanish into the sky became part of the evidence used to understand how the sky itself can change. The fissures of Laki have become part of the landscape now. Their lava has cooled, their vents have weathered, and trails cross the terrain left by the eruption. A place that once reshaped the atmosphere can now be approached as geology, with layers of rock and moss marking where molten material once traveled. The ground carries the memory, even when the surface gives little impression of what happened there. The wider volcanic system remains active. Grimsvötn, the central volcano associated with the Laki fissures, has erupted repeatedly in recent history, including in 1996, 1998, 2004, and 2011. The last of those eruptions lasted about a week and produced an ash plume that reached roughly 20 kilometers, which is about 12 miles, into the atmosphere. For several days, ash spread beyond the immediate region, reminding Iceland that the system beneath the ice is still capable of changing the air above it. Another Icelandic eruption made that connection familiar to the modern world. In 2010, Eyjafjallajökull sent ash into European air routes, leading to widespread flight cancellations and disruptions. The eruption was far smaller than Laki, yet its effects reached across national borders because aircraft depend on an atmosphere that volcanic particles can temporarily make hazardous. The episode offered a modern glimpse of a principle that Laki had demonstrated on a far greater scale. The geological record reaches farther back than written history. Around 939, the Eljaf fissure eruption produced roughly 20 cubic kilometers of lava and tephra, which is about 4.8 cubic miles of material. It belongs to the Katla volcanic system rather than the Grímsvötn system, so it is important to separate the two when tracing Iceland's largest eruptions. The immense event still shows how Icelandic fissure systems can operate on scales far beyond an ordinary volcanic episode. That history also changes the meaning of recurrence. Large eruptions do not arrive according to a dependable calendar, and a past interval cannot provide a date for the next one. Grímsvötn itself has erupted about 70 times during the last 1100 years, while its activity moves through periods of greater and lesser frequency. The Laki fires remain the youngest confirmed large effusive eruption of the system, but geology offers no promise that another event of comparable size must wait for a particular number of centuries. For Icelandic volcanologists, the task is therefore less about predicting a year than recognizing changing conditions. Earthquakes, ground deformation, volcanic gases, surface changes, and other signals can reveal that magma is moving. Instruments can watch the system continuously, building a picture that earlier generations could never have possessed. The purpose is measured and practical: to gain time for warnings, decisions, evacuations, and preparations before an eruption grows beyond its source. Laki belongs to a landscape that is still being written. Its fissures mark an old disturbance, while the surrounding volcanic system continues its own restless cycle. The same Earth that preserved the traces of 1783 continues to generate new signals, new measurements, and new lessons. For those watching Grímsvötn today, the important question is never written into a calendar. It lives in the changing pattern of the Earth itself, where warning depends on noticing movement before movement becomes eruption. If Laki erupted into the world of today, its reach would unfold through systems that did not exist in 1783. Iceland would still be the starting point, but the consequences would travel through aircraft routes, food markets, electrical networks, shipping schedules, and farms separated by oceans. Billions of people depend on these systems every day, which means a disturbance in the atmosphere could become a disturbance in ordinary life, far from the volcano itself. Commercial aviation would be among the first systems to feel the change. Volcanic ash can damage aircraft engines, while sulfuric aerosols create additional atmospheric hazards at cruising altitude. A Laki-scale eruption sustained for months could produce widespread flight restrictions across the Northern Hemisphere, disrupting passenger travel and air freight at the same time. In 2010, Eyjafjallajökull demonstrated how a much smaller Icelandic eruption could interrupt European aviation. A larger and longer event would create a very different logistical problem, with delays spreading through networks that depend on tightly coordinated schedules. Food would present another layer of vulnerability. Modern agriculture can produce enormous quantities of grain, yet production depends on fuel, machinery, fertilizers, irrigation, refrigeration, transport, and international trade. A cooler growing season across several agricultural regions could arrive while farmers were already committed to planting schedules designed around expected temperatures and rainfall. Even a moderate reduction in harvests could raise prices rapidly when multiple producing regions were affected at once. The structure of modern food distribution adds another complication. Grain can cross oceans before reaching a bakery, while livestock feed, fertilizers, fuel, and replacement parts may come from entirely different countries. A disruption in one part of that chain can amplify pressure elsewhere. Markets would respond through prices long before physical shortages reached every household, creating a financial signal that could move around the planet faster than the atmospheric disturbance itself. Human health would also become part of the equation. Sulfuric acid aerosols can irritate the respiratory system and affect the eyes and lungs, while volcanic pollution can interact with existing sources of fine particulate matter. Modern monitoring would allow scientists to identify dangerous air masses and issue warnings with a precision unavailable to people in the 18th century. Satellites, aircraft measurements, ground stations, and atmospheric models could track the movement of the plume across borders and provide a shared picture of what was happening. That knowledge would be enormously valuable, yet information cannot remove the particles from the atmosphere. Modern technology can forecast their movement, reroute aircraft, adjust agricultural planning, coordinate emergency responses, and help governments prepare for shortages. It cannot make sunlight reach the ground once volcanic aerosols have scattered part of it, nor can it instantly replace crops lost across several regions. This creates a strange modern vulnerability. The world is more informed than the world Laki entered, more connected, and far better equipped to measure atmospheric change. Those same connections also allow disruptions to travel through systems built for efficiency rather than isolation. A volcanic eruption in Iceland could still begin as a geological event, then become an atmospheric event, then a transportation problem, a food problem, and an economic problem. The difference is that today, each layer would be linked to millions of others, forming a chain that could move through modern life with extraordinary reach. The idea begins with a strange resemblance between a laboratory proposal and an event that unfolded above Iceland centuries ago. Climate scientists and governments have debated deliberately placing sulfur aerosols in the stratosphere, the high layer of atmosphere where particles can remain suspended and influence how much sunlight reaches Earth. This approach is known as stratospheric aerosol injection, and it is often grouped under the broader term solar geoengineering. The physical principle is familiar from Laki. Sulfur released by a powerful eruption can become sulfuric acid aerosol, forming particles that scatter incoming solar radiation. Some of that sunlight is redirected before it can warm the surface, lowering temperatures across large regions. Laki produced this effect without planning, instruments, or any intention to alter climate. A future intervention would attempt to create a related effect deliberately, with aircraft or other delivery systems placing material at carefully selected altitudes. Historical estimates suggest that Laki released roughly 122 million tons of sulfur dioxide. The resulting atmospheric disturbance contributed to cooling across the Northern Hemisphere for more than a year, with temperatures falling by approximately 1 degree Celsius or 1.8 degrees Fahrenheit in broad, regional, and seasonal measurements. That scale is important because it shows that atmospheric chemistry can influence climate far beyond the location of the original release. The attraction of the modern proposal comes from that same physical power. If warming continues, introducing reflective particles into the stratosphere could, in theory, offset part of the heating by reducing incoming solar energy. The effect could appear comparatively quickly when measured against the much longer timescales of carbon dioxide accumulation and natural climate change. For governments facing severe warming, that speed is one reason the idea remains part of serious scientific discussion. It could also alter precipitation, atmospheric chemistry, and sunlight reaching ecosystems, creating regional effects that may be difficult to predict from a single global temperature number. Laki also provides a record of what becomes difficult once such material enters the atmosphere. The cooling would not necessarily be distributed evenly. Rainfall patterns could shift, some regions could cool more than others, and agricultural conditions could change in ways that differ from the global average. Sulfur compounds can also contribute to acid deposition, while changes in sunlight can affect ecosystems adapted to particular seasonal conditions. There is another concern with no easy reset button. A stratospheric aerosol layer would eventually settle or transform, but maintaining its cooling influence would require repeated injections. If a program continued for many years and then stopped abruptly, accumulated greenhouse warming could return rapidly as the artificial cooling faded. Scientists refer to this potential phenomenon as termination shock. The possibility means that a temporary intervention could create a long-term obligation, tying future societies to decisions made decades earlier. Laki therefore occupies an unusual place in climate science. It was an accidental experiment conducted by a volcano, recorded imperfectly by people who did not understand the full atmospheric mechanism. Today, scientists can study the event with measurements, models, and atmospheric chemistry. The same history that reveals how effectively sunlight can be scattered also reveals how difficult it would be to control every consequence. Laki offers a natural demonstration of the power of atmospheric intervention, along with a reminder that changing the planet's energy balance can never be reduced to one simple adjustment. Survival in Iceland during the months after Laki was measured in small decisions repeated from one household to another. The famine became known as the Famine of the Mist, and it killed roughly 1 in 5 Icelanders. That figure is severe, yet it leaves another part of the story in view. 4 in 5 survived. They did so on a remote island under Danish colonial rule, with trade restricted, pasture damaged, livestock dying, and an eruption that continued for 8 months. Their survival depended on adaptation rather than a single act of endurance. Families watched the condition of their animals and changed where they grazed them whenever safer ground could be found. Livestock near the eruption zone were exposed to fluorine carried in ash and grass. Many animals became sick or died, taking milk, meat, and future breeding capacity with them. Moving surviving animals away from contaminated pasture could therefore preserve more than one season of food. It could preserve the possibility of rebuilding. Food also came from the sea. Fishing continued through the difficult summer, maintaining a source of nourishment when farming could no longer be trusted. A strong salmon run in the summer of 1783 brought an especially valuable addition to local diets. For communities facing shortages, fish did not replace the lost harvest, yet it supplied protein and calories when other sources were disappearing. Such seasonal resources could become a narrow bridge between scarcity and starvation. The geography of Iceland offered another form of resilience. Distance could become a burden during shortages, yet it also created separation between communities and the worst concentrations of contamination, leaving pockets of relative stability where assistance could begin. Farms were scattered across the island, separated by difficult terrain and long distances. That distribution meant the disaster did not strike every district with identical force. Some communities suffered heavier contamination, while others retained more usable pasture, animals, or food. Support could then move between neighboring settlements, carrying supplies, information, or surviving livestock. A dispersed society could absorb local losses differently from a population concentrated around one vulnerable center. Pastor Johann Steingrimson became part of that practical response. His role extended beyond the pulpit as he helped organize rationing, appealed for assistance, and maintained cooperation among people facing months of uncertainty. His records preserved details of hunger, illness, livestock losses, and the choices communities made to keep functioning. The account offers something rare in disaster history, a view of resilience while the disaster was still unfolding. Help eventually arrived from the Danish authorities. Food shipments came late, and they were far from sufficient for the scale of the crisis, yet even limited supplies could create a crucial margin for households already living close to exhaustion. The route was imperfect, shaped by the inequalities of colonial rule, but it provided a connection through which outside resources could reach the island. The legacy of Laki, therefore, rests partly in what survived with the people themselves. Icelanders inherited practical knowledge about volcanic hazards, contaminated land, livestock protection, food storage, and community coordination. The lesson was carried through generations as a working understanding of an active landscape. The island could be damaged on a scale no household could control, while survival still depended on choices made together: one pasture, one boat, one ration, and one neighboring farm at a time. Jon Steingrimson died in 1791, 8 years after the eruption had begun. By then, the fire had become part of his life story, and he had already written about it in two forms. One was his autobiography, where the disaster occupied a central place. The other was his fire treatise, a detailed account created with the fear that such an experience might fade from memory as the people who witnessed it disappeared. The treatise remained a manuscript for 132 years. It passed through his family, survived in handwritten copies, and waited beyond the lifetime of the man who had composed it. In 1913, it was finally printed. By that time, the world that had witnessed the eruption was gone, and the science of volcanology had developed instruments and methods that Steingrimson could never have imagined. His pages nevertheless contained something those instruments could not provide: a continuous witness account from within the disaster itself. He had recorded the eruption as a sequence of events witnessed from the ground, noting when different phases began, where lava moved, and how the landscape changed around him. He described the dates of fissure openings and the behavior of individual lava flows, preserving a chronology built from direct observation. His account gave later researchers a human timescale for an eruption that had otherwise survived mainly through scattered physical traces. When modern volcanologists compared his observations with geological evidence, the old record became unexpectedly precise. Ice cores preserve layers of volcanic material and chemical signals carried through the atmosphere. Tephra deposits preserve fragments of erupted material within sediments and soils. These physical archives can establish when major events occurred, while Steingrimson's testimony adds the sequence and local detail that geology alone cannot recover. The two forms of evidence can meet across centuries. That continuity gave later scholars a rare bridge between lived experience and physical evidence. His writing continues to appear in scientific studies because the information is specific enough to remain useful. More than 2 centuries after the eruption, researchers can still examine his descriptions of lava movement, eruption timing, environmental change, and human experience alongside modern geological reconstructions. A manuscript created with 18th century materials has become part of a scientific record extending into the 21st century. Steingrimson also interpreted what he witnessed through his faith. He believed that the movement of lava could be understood as divine intervention and that prayer had a role in the survival of his community. Those interpretations belong to his time and to his personal understanding of catastrophe. They exist beside the observations themselves. A person can describe where a lava flow traveled with remarkable accuracy while explaining its meaning through a theological framework. The two layers of his account do not erase one another. That distinction is part of what makes his record enduring. Scientific evidence does not require every observer to possess modern theories. It requires observations that can be examined, compared, and tested against other evidence. Steingrimson supplied those observations when almost no instruments were available to do so. He feared that memory would disappear with the people who carried it. The manuscript waited for 132 years, and when science finally returned to its pages, the record proved difficult to replace. Some disasters announce themselves with a single instant. A mountain collapses, water crosses a shoreline, a structure gives way, and the boundary between before and after can be drawn almost immediately. Laki belonged to another kind of disaster, one that spread through time until its separate pieces became difficult to recognize as parts of the same event. Its consequences moved through air, pasture, weather, harvests, and human health, each following a different rhythm. The lava could be seen. The deeper hazards could not. Fluorine settled onto vegetation and entered the bodies of grazing animals without producing a visible signal that a farmer could follow. Sulfuric aerosols traveled through the atmosphere far from Iceland, where people encountered their effects as respiratory illness and altered weather. In Britain, 23,000 excess deaths were associated with the polluted conditions of the summer of 1783. Yet the people experiencing them had no way to connect their suffering with a volcanic fissure far away. For a farmer, the evidence arrived as a series of bewildering changes. Animals weakened, teeth and bones deteriorated. Pastures that appeared ordinary became dangerous sources of food. Elsewhere, a person with severe breathing trouble could look out at a familiar landscape while the atmosphere carried material from an eruption they had never heard of. Each observation made sense within its immediate surroundings, while the larger pattern remained outside the reach of ordinary experience. The same separation appeared in the weather. Cooling did not arrive with a visible boundary across the sky. A colder season could resemble an unfortunate turn in ordinary weather, especially when measured against the limited records available to people at the time. Harvests suffered in different places for different reasons, and food shortages developed through a chain of failed expectations. A poor crop became higher prices. Higher prices changed household choices. Scarcity placed pressure on communities and governments. One consequence prepared the ground for another. Distance made the pattern harder to recognize. The eruption began in Iceland, while its atmospheric effects reached across the North Atlantic and into continental Europe. The affected systems were connected, yet the people within them experienced only fragments. One community saw sick livestock, another endured respiratory disease, another watched crops fail. Someone else faced rising food costs. Few could see these events as separate expressions of one disturbance moving through the Earth system. That difficulty has shaped the way Laki is remembered. Human memory favors events with a clear center, a visible source, and a recognizable ending. A destructive wave leaves a physical mark. An earthquake creates ruins. A major eruption can fill the sky with ash and become an image preserved for generations. Laki offered fewer such moments. Much of its damage arrived through processes too gradual, distant, or technical to become a single shared picture. The absence of a visible shape did not make the catastrophe smaller. It made the catastrophe harder to name. Its causes crossed boundaries between geology, atmospheric chemistry, agriculture, medicine, and society, disciplines that would only much later develop the language needed to connect them. For those living through the crisis, there was no complete map of the chain surrounding them. There were only symptoms, losses, strange seasons, empty fields, and changing prices, each appearing separately as the larger pattern continued beyond ordinary sight. A society can appear secure for years, while depending on a surprisingly narrow space between stability and shortage. That space is the margin. Laki revealed how quickly such a margin can disappear when several pressures arrive together, and the lesson reaches far beyond 18th century Iceland. For Icelandic farmers, the crucial reserve was livestock. Herds provided milk, meat, labor, and the means to rebuild after difficult seasons. When volcanic fluorine entered the grazing system, that reserve began to fail. Animals weakened, breeding stock was lost, and food production contracted. A system that had functioned through ordinary hardship suddenly had very little room left for another setback. France carried a different margin. Grain sat at the center of daily survival, and an adequate harvest could keep households supplied even when taxes, prices, and political tensions were already creating strain. Once harvests failed repeatedly, the distance between an unhappy population and a food crisis became much smaller. Scarcity raised prices, expensive bread consumed household income, and every additional disruption became harder to absorb. Modern societies possess buffers that 18th century communities could scarcely imagine. Grain can cross oceans. Governments can coordinate emergency assistance. Food can be stored, transported, and redistributed across continents. Weather observations can be shared almost instantly, while atmospheric measurements allow scientists to trace disturbances as they develop. These capacities create forms of resilience that earlier generations did not possess. Efficiency, however, has changed the shape of the margin. Modern agriculture often depends on tightly coordinated supplies of fuel, fertilizer, machinery, transport, refrigeration, and finance. A farm may produce more with fewer reserves because the wider system is expected to provide whatever is needed at the right moment. Warehouses and inventories can therefore become smaller, while dependence on uninterrupted movement becomes greater. The same pattern extends into the movement of food itself. A shipment delayed at one port can affect processors somewhere else. A shortage of fuel can increase transport costs, alter fertilizer prices, and raise the cost of cultivation. A disruption in one region can reach another through markets that connect producers and consumers across enormous distances. Interconnection spreads assistance, yet it also gives disruption more pathways. This does not make the modern world identical to the world of 1783. It makes vulnerability harder to judge by appearances. A society may possess extraordinary technology while relying on systems with little tolerance for prolonged interruption. The visible abundance of a normal year can conceal how many separate processes must continue working for that abundance to remain available. That room can exist as stored supplies, spare capacity, alternative routes, stronger local networks, or time to adapt. Its value becomes visible only when ordinary assumptions stop holding. The margin, then, is not a fixed amount of wealth, food, technology, or stored material. It is the distance between ordinary demand and the point where a system begins to lose its ability to recover. Every society carries such a distance, whether it is measured in grain reserves, fuel supplies, medical capacity, transport availability, or time. Laki showed what happens when several margins narrow together. The lesson belongs to every complex society because resilience is never only about having more. It depends on having enough room for something unexpected to happen without turning one failure into many. The margin has changed shape across centuries, but the need for one remains. A moment at the edge of Steingrimson's church can hold two explanations without requiring one to erase the other. On July 20th, 1783, lava approached the church and stopped within a short distance of the building. To the congregation, the interruption carried the unmistakable meaning of divine intervention. Steingrimson understood the event through faith, and his sermon transformed the episode into part of a larger spiritual account of the disaster. Geology offers another description. Lava flows respond to changes in pressure, supply, terrain, and the movement of molten rock beneath the surface. When the supply feeding a flow weakens or pauses, the advancing front can lose its momentum and stop. The physical process requires no supernatural mechanism to explain it. At the same time, identifying that process does not erase what the moment meant to the people standing nearby. This is where history becomes more interesting than a choice between belief and science. A physical event can possess a measurable cause while carrying a separate layer of human meaning. The lava stopped through the behavior of a volcanic system. Steingrimson stood before his congregation during an extraordinary crisis, spoke within the language of his age, and helped preserve a sense of order while familiar structures of life were breaking apart. For an 18th century observer, the boundaries of natural science were narrow. There were no modern instruments for measuring atmospheric chemistry across continents, no satellite images tracing ash and aerosols, and no established theory describing how volcanic eruptions could alter climate. Religious interpretation, therefore, occupied intellectual territory that modern science has gradually filled with other kinds of explanation. Calling the event an act of God was not an escape from observation. It was a framework for placing observation inside a meaningful world. A different kind of framework appeared across the Atlantic. Benjamin Franklin considered the effects of volcanic material in the atmosphere and proposed that a veil of suspended particles could alter sunlight and temperature. His interpretation belonged to an emerging tradition of natural philosophy, where observations were increasingly connected through physical processes. He was working with the evidence and concepts available to him, just as Steingrimson was working with his own. Neither man possessed the complete picture. Steingrimson could record the movement of lava, the condition of animals, the changing landscape, and the suffering of his parish with unusual precision. Franklin could recognize a connection between volcanic material and atmospheric change without knowing the full chemistry involved. Their observations survived because they were careful, specific, and rooted in what they could actually perceive. The distance between their explanations is therefore less about intelligence than about the tools of understanding. Every generation inherits a vocabulary for making sense of reality, then expands it through measurement, experience, and accumulated evidence. Ideas that seem complete in one century can become partial in another, while observations made centuries earlier can remain valuable long after their original interpretation has changed. Steingrimson's theology and Franklin's volcanic theory belong to different explanatory worlds, yet both emerged from an attempt to give shape to events that exceeded ordinary experience. The facts endured beneath those frameworks. What changed was the language through which people could understand them. The same process continues today, as new instruments reveal relationships that earlier observers could sense but could not yet describe with precision or test through controlled evidence. History often arrives in books as a sequence of decisions. A king makes a choice, a crowd gathers, An assembly votes, a government falls, and the consequences are arranged into a line that seems to explain itself. Laki makes that line harder to draw. The people who gathered in Paris in 1789 were responding to immediate political and economic realities, while a much older physical process had already altered some of the conditions surrounding them. No revolutionary pamphlet needed to mention an Icelandic fissure. The deputies who helped create the Declaration of the Rights of Man were concerned with representation, taxation, privilege, law, and sovereignty. The French monarchy had accumulated enormous debts. The tax system placed heavy burdens on ordinary people, and Enlightenment ideas had changed the language of political authority. These forces belonged to human institutions and human choices. Food added another layer. Harvest failures, grain shortages, and high bread prices narrowed the space in which those institutions could respond. The agricultural system had less resilience when another poor harvest arrived. Laki did not create every weakness within France, and it did not determine the decisions made by kings, ministers, deputies, or crowds. Its influence belonged to the conditions surrounding those decisions, where atmospheric changes could become crop stress could become scarcity, and scarcity could become social pressure. That distinction matters because history is often organized around visible human actions. A revolution has speeches, crowds, battles, laws, prisons, and executions. Those leave documents that can be dated, named, and placed into a recognizable sequence. Atmospheric chemistry has no parliament. A damaged harvest has no author. A colder season does not sign a decree. Yet these forces can alter the circumstances in which political decisions are made. The same pattern appears far beyond France. Human societies depend on rainfall, soil, rivers, forests, fisheries, disease environments, and the stability of the atmosphere. These systems operate according to physical and biological processes that continue whether governments understand them or not. Their effects can remain outside the historical narrative until a disruption becomes large enough to enter written records. Laki, therefore, does not replace political history with environmental history. It adds another layer to the same world. Human beings make decisions, build institutions, create conflicts, and accept or resist change. At the same time, those decisions occur inside a material environment that supplies food, shapes health, limits movement, and determines how much pressure a society can absorb before its systems begin to strain. Responsibility remains human. A volcanic eruption cannot choose a tax policy, write a law, or command an army. People remain accountable for the structures they build and the choices they make within them. Physical conditions, however, influence which choices are available, which pressures become urgent, and how much room remains for compromise. Perhaps this is what makes history so difficult to hold in a single story. The human narrative is only one layer of a larger process. Under every revolution are harvests and weather. Under every settlement are rivers and soils. Under every century are atmospheric and geological systems moving according to rhythms that rarely appear in political chronicles. Laki belongs to that deeper history. Its influence did not enter the revolution as a decision or an intention. It entered as altered conditions, changing the boundaries within which human decisions could unfold. Some disasters leave behind objects that seem to explain themselves. A ruined building, a crater, a field covered in ash can become a permanent witness. Laki left such evidence in abundance. The lava remains across about 1,450 square kilometers, which is about 560 square miles, of Iceland, hardened into basalt and preserving the path of an eruption that unfolded for months. Anyone walking across those surfaces can see where molten rock once moved through the landscape. The more consequential parts of the disaster are harder to hold in the mind. The people who died in Britain during the summer of 1783 left no physical mark that identifies Laki as the cause. Their illnesses could resemble other diseases of the season. Contemporary observers described unusual sickness, breathing difficulties, and widespread distress, yet the connection to a volcanic eruption was far beyond the medical framework available to them. Families buried their dead without a name for the force that had reached them from across the sea. That distance makes the history especially difficult to reconstruct. The path from an Icelandic fissure to illness in Britain passes through atmospheric chemistry, weather patterns, and human exposure. Another path leads toward agricultural stress in Europe, where unusual seasons affected crops and food prices. None of these chains existed as a single story in the records of the time. They survived as fragments, separated across places, institutions, and kinds of evidence. Modern researchers can bring those fragments together. Ice cores preserve layers of volcanic material and chemical changes in the atmosphere. Parish records preserve deaths and observations from communities far from Iceland. Historical weather records reveal patterns that became meaningful only when compared across regions. Economic records show changes in grain prices and availability. Atmospheric models can then test whether the physical mechanisms connecting these observations are consistent with what is known about volcanic emissions. This kind of reconstruction changes the meaning of evidence. A death certificate may contain no mention of a distant eruption. A harvest record may describe poor yields without identifying their atmospheric cause. A weather observation may appear ordinary when viewed alone. When these records are placed alongside geological evidence, however, separate details can form a connected sequence. The catastrophe becomes visible through relationships among traces that were never intended to tell the same story. There is something deeply human in that process. The people living through the eruption did not possess instruments capable of tracking the movement of volcanic gases across continents. They could observe the symptoms, the failed harvests, the strange weather, and the losses around them. They could record what happened in their own communities. What they could not see was the larger system linking those experiences together. That limitation does not make their accounts less valuable. It makes them more important. Their records preserve the local pieces from which later generations can build a wider understanding. Science can connect those pieces across time, but the original observations still belong to the people who lived them. Laki therefore survives in two forms. One is written across the Icelandic landscape in stone. The other exists in records, patterns, and traces that only become legible when different kinds of knowledge meet. The lava tells us where the eruption reached. The scattered human records tell us how far its consequences traveled. A volcano has no calendar. Deep below Iceland, pressure gathered within the Grímsvötn volcanic system until molten rock found pathways through the crust. The process followed its own physical limits, governed by heat, pressure, and the movement of material inside Earth. Human lives were present above it, but they were never part of the mechanism. The fissure that opened across 27 kilometers, which is about 17 miles, belonged to a much older planetary rhythm. The forces capable of splitting the crust are also involved in creating mountains, shifting continents, and renewing the surface of the planet. The same broad machinery helps return carbon to the deep Earth, alters landscapes, and contributes to the long geological balance that has allowed life to persist. For a person standing on the surface, these processes can seem immense because a human lifetime provides such a narrow window through which to observe them. A volcanic eruption may occupy months, while the tectonic movements behind it unfold across thousands or millions of years. Continents drift by small amounts each year. Ocean basins open and close over spans that exceed recorded history by extraordinary margins. Against that scale, 8 months of eruption becomes a brief disturbance within a much older sequence. Human societies naturally place themselves at the center of events. A failed harvest becomes a political crisis. A famine becomes a family memory. A volcanic cloud crossing a sky becomes a sign, an omen, or a scientific observation. Those interpretations matter because they describe how people inhabit the world. The geological process beneath them belongs to another order entirely. There is a strange humility in holding both views together. The deaths caused by the eruption were real. The suffering of Icelandic families was real. The food shortages that intensified hardship across Europe were real. None of those realities become smaller when placed beside the age of the planet. They become part of a larger physical setting in which human life is both vulnerable and persistent. Earth itself does not need to be imagined as hostile. Its crust moves because heat escapes from its interior. Magma rises because differences in pressure and density drive it upward. Volcanic gases enter the atmosphere because the planet has pathways through which material travels from depth to surface. These processes existed before human beings could name them, and they will continue after our present languages, borders, and institutions have changed. Our civilization occupies only a thin interval within that story. Modern humans have existed for a fraction of geological time, while agriculture and cities are far more recent still. Written history captures thousands of years, yet the rocks beneath our settlements preserve chapters measured in millions and hundreds of millions of years. Seen from that distance, Laki becomes more than a story about destruction. It becomes a meeting point between two scales of existence. One belongs to people, measured in generations, harvests, memories, and names. The other belongs to Earth, measured in pressure, fracture, cooling, burial, uplift, and time. We live inside that larger system, dependent on its stability while remaining exposed to its movement. The ground beneath a village can support generations of ordinary life, then change in ways no human intention requested. There is no cruelty in that process, only a physical world continuing according to rules older than us. Laki offers no message of its own. The Grimsvötn system did not gather magma with a lesson in mind, and the crust did not fracture according to human need. Pressure accumulated until the conditions for rupture were met. The eruption followed the physical character of the planet, indifferent to the people living above it. What remains for us is different. Human beings are creatures that turn experience into memory, and memory into preparation. Laki shows why that process matters. Some of the most consequential disruptions can develop without a single moment that clearly announces their arrival. A volcanic eruption may begin with fire, yet its wider consequences can travel through air, crops, markets, illness, and political strain long after the first spectacle has passed. That pattern reaches beyond volcanoes. Modern societies depend on systems whose parts are linked so closely that trouble in one place can move through many others. Food depends on transport, energy, fertilizer, storage, labor, and weather. Hospitals depend on electricity, medicines, supply networks, and trained workers. Cities depend on water, communications, fuel, and infrastructure. Each system can appear strong while resting on margins that are thinner than they seem. Laki also gives value to patient observation. The people of Iceland could not measure atmospheric chemistry across the Northern Hemisphere, yet they recorded what happened around them. Steingrimson preserved dates, physical changes, human suffering, and the sequence of events as carefully as he could. Centuries later, those observations became part of a much larger reconstruction. The lesson is not that every record will reveal the future. It is that careful records allow later generations to understand what earlier generations could only experience. Modern monitoring extends that ability. Satellites can observe volcanic plumes. Instruments can detect changes in the ground. Atmospheric models can follow gases and particles as they spread. Agricultural data can reveal stress across regions, while communication networks can move information across continents within moments. These capabilities create opportunities that 18th century communities never possessed. They also change the meaning of warning. A signal can arrive before the damage becomes obvious, allowing decisions to begin while choices still exist. That interval can be precious, especially when disruption moves through several connected systems at once. Capability, however, is different from resilience. Knowing that disruption is spreading does not automatically create food, restore transport, protect crops, or coordinate governments. Preparation requires reserves, alternative routes, shared information, and institutions capable of acting before pressure becomes collapse. The strength of a society is measured partly by what remains available when ordinary systems begin to fail. Steingrimson's work gives this reflection a human scale. He feared that the experience would disappear from memory, so he wrote. His record survived long enough for later generations to read it, test it against physical evidence, and find details that could not be recovered elsewhere. Memory became evidence, and evidence became understanding. 2 centuries later, the work continues. Laki cannot be changed, prevented, or negotiated with. Its value lies in what can be carried forward from it. A wider margin, a better record, earlier recognition, stronger cooperation, and a willingness to notice slow changes before they become overwhelming are all forms of resilience. The ground beneath Iceland followed its own laws. The people above it had to learn how to live within them. That remains the enduring human task. Jon Steingrimson's final pages carry the weight of someone who has spent months watching ordinary life become difficult to recognize. His fire treatise does not close with a neat resolution. It preserves observations, dates, losses, prayers, and the changing character of the eruption. His task was limited to witnessing and recording. The world around him continued according to forces beyond his reach. Today, the fissures themselves have become places people can visit. The lava has cooled into a broad field of basalt, marked by craters, ridges, and long fractures that preserve the path of molten rock. Vegetation has returned across portions of the terrain, while other stretches remain dark and spare. The landscape can appear almost permanent, as though the eruption belongs entirely to the past. Yet the rock is only the surface of a much older process. Far below the ice of Vatnajökull, the Grímsvötn volcanic system remains active. Magma continues to move through the crust, heat continues to rise, and pressure changes within the system can be detected through instruments placed across the region. The eruption of 2011 released part of that stored energy, producing one of Iceland's largest eruptions in recent decades. Such an event does not reset the geological system to zero. After an eruption, magma can begin accumulating again, and the cycle continues according to the movement of Earth's interior. Modern instruments give this process a kind of measurable presence. Seismometers record small earthquakes that accompany movement underground. Global positioning equipment detects subtle changes in the shape of the ground. Scientists also watch geothermal activity, changes in ice, and other signals that may reveal alterations within the volcanic system. None of these observations provides a simple timetable. They create a record of changing conditions, allowing researchers to distinguish ordinary fluctuations from patterns that deserve closer attention. Each measurement becomes another small piece of a living geological record. That knowledge would transform the circumstances surrounding another major eruption. Satellites could follow an atmospheric plume across continents. Weather models could estimate where sulfur compounds might travel. Communication networks could distribute warnings within minutes, while agricultural agencies could compare crop conditions across distant regions. Governments would possess tools for coordinating food reserves and emergency assistance on a scale that 18th century communities could never have imagined. Still, modernity carries its own exposure. The world now contains more than 8 billion people, and enormous populations depend on food systems that cross oceans and borders. A disruption in one region can become a problem somewhere else through transport, markets, energy supplies, and fertilizer production. Better information can shorten the distance between observation and response, yet greater interconnection can also shorten the path by which disruption travels. That is the strange character of the Laki landscape today. Visitors can walk across rock formed during the eruption, tracing fractures that opened generations ago. The ground feels solid beneath their feet, fixed into a landscape that seems finished. Geological time has a different rhythm. The surface records what happened, while the system below continues to change, accumulating heat and pressure without regard for the human calendar. Steingrimson could preserve only what he witnessed. We have instruments that can observe what lies beyond ordinary sight. The difference is profound, yet the underlying world remains the same, moving according to processes that began long before any record was written. Steingrimson's record survived in a way that the eruption itself never could. The lava remains across Iceland. The altered landscapes can still be traced, and geological evidence preserves the physical story. Yet those records cannot describe what a person saw on a particular day, what changed from one eruption episode to the next, or how the surrounding community understood events as they unfolded. His pages carry that human scale alongside the geological one. Much of the written world of 1783 has disappeared. Papers decay, collections scatter, families change, and memories lose their detail as generations pass. Steingrimson's manuscript endured through his descendants, who kept copies within the family, until it was eventually published in 1913. By then, more than a century had passed since the eruption. The survival itself was improbable, but preservation alone would not have made the document important. Its lasting value came from the precision of what had been written inside it. Steingrimson recorded sequences. He noted when fissures opened, how the lava advanced, how conditions changed around the eruption, and how environmental effects appeared in the community. Such details gave later scientists something unusual, an eyewitness chronology that could be compared with physical evidence. Ice cores preserved layers of volcanic material and chemical changes in the atmosphere. Deposits of volcanic ash marked episodes of activity. The written account could be placed beside those traces, allowing different kinds of evidence to speak to one another across centuries. That is where the record became larger than its original purpose. Steingrimson had no instruments capable of measuring atmospheric chemistry, seismic movement, or the composition of distant deposits. He could not have known how future scientists would investigate volcanic eruptions. What he could do was observe carefully, distinguish one event from another, and place his observations into a sequence. Those modest acts gave later researchers a structure against which other evidence could be tested. His understanding of the eruption also belonged to his own century. He interpreted events through theology and regarded divine intervention as part of the meaning of what he witnessed. Modern volcanology uses different frameworks, drawing on physical processes, atmospheric chemistry, geology, and chronology. The difference does not erase the observations. A person can understand an event through one intellectual world while leaving behind evidence that remains useful within another. More than 2 centuries later, his record continues to appear in scientific discussions because first-hand observations of a major eruption are rare, especially observations detailed enough to be compared with independent evidence. The manuscript became a bridge between lived experience and scientific reconstruction, carrying information across a span of time that Steingrimson could never have pictured. The ground around Laki records the eruption in stone. Ice preserves traces in distant layers. Archives preserve fragments of human memory. Steingrimson added another kind of record, one made from attention itself. He wrote for people he hoped would remember. Scientists eventually read him for reasons he could not have imagined. That may be the most enduring part of his work. The eruption passed, the famine passed, the political world that surrounded the disaster changed beyond recognition. The record remained, specific enough to be checked, studied, and understood anew. In that sense, preservation became a form of continuity, allowing a voice from one century to enter another without needing to become anything other than an accurate witness.